This is section 9.3 from Code HS, Encoding with Binary. Just a reminder that tonight is when your program is due and your written response for Hangman. Make sure it's all done. For the written response, if you need help, go to Unit 8, slides from the 3B section. Those can help you. You should probably either way have them open while you're going through so that this way you can compare side by side. Remember, I put a lot of good helpful hints on there for the written response. All right, so to the lesson, encoding with binary. Remember from yesterday, the binary number system only has 2 digits, 0 or 1 that we can use. All computers store their data in binary. So computers, that is all they read, are all these series of zeros and ones. The binary number system, the place values that we were dealing with yesterday, the ones place, the twos place, the fours place, the eights place, this is what we refer to as a binary digit, or more commonly used, a bit. So each specific place value, which is what we call a bit, can either hold the value 0 or 1. So here's just showing you some place values. So starting on the right, there's the ones place value, which is its own bit. Then comes the twos place value, which is its own bit. Then the fours place value, which is its own bit. The eights, which is a bit. And then the 16ths, which is a bit. So each one is on its own considered a bit. So right now I am showing you 5 bits. There are 5 place values there, so there's 5 bits. Each specific place value holds only a 0 or a 1 at any given time. So here we have the binary number 1101, which in our decimal form would be the number 13. But as a binary here, 1101, this is using up 4 bits right now to write this number because there's 4 place values that we're using. On the computer, when we're using characters, so the different letters, your entire keyboard is made up of characters. The capital A, in our heads, we're thinking, oh, we're just hitting a capital A. But the computer is actually reading it here as 01000001. That alone is requiring 8 binary digits. There's 8 numbers there that are representing the letter A. So that's really 8 bits to represent that one single character on the computer. So we think we're typing in that one simple character. We're really hitting something and it's taking up 8 bits on the computer. Why are we using so many bits? Well, 1 bit only has 2 possible values. So if we're only using the ones place, the only options are a 0 or a 1. Those are our only possible values. If we have 2 bits, we now have 4 possible values. So if we're going to use only the ones place and the twos place, we can do 0, 0, we can do 0, 1, we can do 1, 0, we can do 1, 1. 3 bits, we now have 8 possible values. So if we're going to use the ones place, the twos place, and the fours place, now we have 8 different ways that we can represent something. We can represent something as 000, 001, 010, 011, and so on. What if we had 4 bits? Is this now going to go to 16 possible values if we follow the pattern that we've been seeing? Maybe. So let's notice what happens when we added the 1 bit. So if we went from the 2 to the 4, so the first option for 2 bits could have been 0, 0. When I added in that 3rd bit, so now we have the 4's place in here, that 0, 0, that 4's place can now hold a 0 or a 1. So it just doubled in how many possible values I had. When it's 0, 1 from before, and I add in that 3rd bit now, that 0, 1 could now have the 0 before it again, or the 1. So I just took the 0, 1 and doubled how many I had again. Same thing if it was the 1, 0. I now just doubled the possible values by adding in that extra bit. Same thing when it was the 1, 1 possibility from the 2 bits. When I added in that extra bit, again, it just doubled the possible values that I had. So if each possible value with 2 bits doubled when we added in a 3rd bit place value, will that happen again for 4 bits? Will we take the 3 bits, which was 8 possible values, double it, and now have 16 possible values? The answer is yes. So every time you add in a new bit, you are doubling the number of possible values you could possibly represent. 1 bit, there was 2 possible values. 2 bits, using up 2 bits, 2 place values, there was 4 possible values, and so on. So 5 bits after this would have 32 possible values. 6 bits would have 64 possible values, and so on. What pattern do you notice here with the possible values? So we went with 2 to 4 to 8 to 16. Based off of our place values from yesterday, we should hopefully recognize that these are our powers of 2. Only this time we are skipping the 0 power when we're talking about the possible values. So the first one, 2 possible values, was really 2 to the first. 4 possible values is 2 to the second. 8 possible values is 2 to the third. 16, 2 to the fourth. If we compare the power to the number of bits, they are equal. So if you have 2 bits, you have 2 to the second possible values. When you had 4 bits, there are really 2 to the fourth possible values that you could have. So that's where the 16 comes from. So the number of bits, to figure out how many possible values there are, you're going to take 2 and raise it to the number of bits that you have. That is your number of possible values. So n bits, you're going to have 2 to the n possible values. 2 values for each bit. 8 bits is really going to give you 2 to the 8th possible values, which is 256. 8 bits are actually called a byte. So here's just different groups of bits, and the different examples are different things that they can store and hold. So if you're only using a single bit, a single place value, the best you could do is have this represent really just like a true false. 8 bits is how we get 1 character of text. 2 to the 10th bytes, which remember a single byte is 8 bits. So 2 to the 10th bytes is really 1024 bytes, which is really times 8 for the number of bits, is how we could represent a paragraph of text. It would require 2 to the 20th bytes, which is a megabyte, to hold a 3-minute song, and so on. So the different groups of bits, these are the different names that we have. You really just have to know bit and byte. You really don't have to know that far, but just in case you're interested. All right, so lesson 9.1, we discussed different ways we encode things. Zip codes, area codes, our DNA. Another great example of encoding is the Morse code. So the Morse code here, every letter, this does continue past C, I'm only showing you the first 3, but every letter in the Morse code is represented as a series of quick little dots or long drawn out dashes. If we think about these in terms of zeros and ones, kind of like our binary numbers, the dot and then the dash for A, the dots we can think of as a 0, the long dashes we can think of as an A. So Morse code to translate it into binary, A could be like 0, 1. B, which is the long dash followed by the 3 quick short dots, if you want to convert this into binary, is kind of like having the number 1, 0, 0, 0. C, and so on. Morse code is a binary communication protocol. If everyone agrees upon this encoding, we're able to communicate using only 2 different signals, long and short, or 1 and 0. How does the computer encode the letters of the alphabet using binary numbers, similar to how we do for Morse code? How does the computer do it? How many bits would be required? How many bits do we have to use? Let's say we only had 2 bits. Unfortunately, 2 bits, 2 to the second, only gives us 4 possible values that we can encode. We would have the possible value 0, 0, which we can say is A. We would have the possible value 0, 1, which we can say is B. 1, 0, which we can say is C. 1, 1, which we can say is D. Unfortunately, there are problems with this. Biggest one, we're only representing 4 values. If we want the letters of the alphabet, there's 26 letters in the alphabet, and that's only taking care of either capital case or lowercase. The computer does read capital and lowercase letters differently. So you would need some numbers to represent the capitals, then you would need to do different numbers to represent the lowercase. So really we're up to 52 now. As of right now, no one knows this encoding except for us. In order for it to work, everyone has to agree on an encoding to make it useful, similar to the Morse code. That was a protocol that everyone agreed upon, which makes it useful to communicate, and it worked back in the day. So remember, 1 byte is 8 bits. 8 bits is 2 to the 8th, which is 256 possible values you can make using only zeros and ones. You could have 8 zeros, you could do 7 zeros with a 1, you could do 6 zeros with a 1 0, 6 zeros with a 1 1, and so on. This is enough to store every single character possible. So the capital letters, then you would have the lowercase letters. We would have symbols such as the curly bracket. If you're using 8 bits, which is 256 possible values, you would have enough possible combinations of zeros and ones to store every single character we can possibly use. This is what we call the ASCII table. This is an agreed upon protocol that all computers follow. So here are where you would have your different symbols that you could possibly represent in this far right column. The far left column is the binary number that represents each one of those characters. ASCII is a protocol for encoding text. If all machines agree to use the ASCII symbol, then all machines will be able to correctly interpret text. This includes all possible characters, including a space. So not only is there the curly brackets, a period, a question mark, but the space bar also has its own 8 numbers, 8 digits of zeros and ones that represents the space bar. This is how all computers are able to communicate with one another. So here we have a little sentence in binary. So here we're broken down. There is a little space here between different ones. So we're broken down into chunks of 8. Each chunk of 8 represents a different character. So in order for the ASCII table to work, what this does is each chunk of 8 you would convert, easiest way, into our decimal numbers that we looked at yesterday. Each one of them, you can then go to your ASCII table and figure out what each one of these numbers represents as a character, and therefore translate what that message means. In this case, the result is binary is awesome. So for today, you have a quiz, which is 2 questions talking about bits. Then you're going to create your own encoding. So similar to how that ASCII table works, where you're using different series of zeros and ones to represent the different characters, you're going to create your own encoding. This is on Code HS. It's 9.3.7. The other example that's there is just something that you can look at and play around with. The next few slides, I have helpful hints for you for how to do the encoding exercise, because it could be a little confusing. So if you look through it, that should help you. You only have to do the capital letters and the space bar. You don't have to do anything else. You don't have to do the lowercase letters unless you want to. Just the capital letters A through Z, which is 26, and the space bar, which would be 27 characters you're going to have to create.